Okay, so we are continuing with the chain rule, and I'm trying to do a variety of problems. The book, of course, has good examples, but I try to do some additional examples sometimes so you have a wider variety. So take a moment and copy this example down here, and then we'll talk about the solution. Okay, so for this problem, we want to find the derivative of the function y equals 2 raised to the 3 to the x squared power. So it's, I don't know how, I mean, it's like you got the 2. Well, it's as you see it. You might want to, it might be easier to think of it like this. 2 raised to the power 3 to the x squared. Okay, that's what we are finding the derivative of. And sometimes, I mean, all right. So you know that the power rule okay, the derivative of x to the rth power, and r could be any number, right? Let me just double, I mean, that should be right, but sometimes, just double check that, that should be right. Yeah, any real number, right? R is any real number. So, so you know this rule as the power rule. Can we apply the power rule to this finding the derivative of this function? Well, we're getting a difference of opinion here. Some people think yes, some people think no. Well, the answer is no. And I'm getting, well, hey, you know, Layla, sometimes we'll have 6 people that say no and 1 person that says yes, and the yes person's right. Okay, so can't always go by that. But in this case, and I appreciate all participation, in this case, the answer will be no, because you see, you're taking this 2 here and you're raising it to a power. But 2 is not x, it's not a variable, it's a number. So the power rule here this power rule is not gonna work. So we need to come up with a new rule for a derivative where we take a number and raise it to a power. So to that end, then, we need a formula for the derivative of a to the x power. Okay, a to the x power. You know the derivative of e to the x power. You know, like, for instance, the derivative I see, and okay, well, I understand. We know the derivative of e to the x is e to the x. But that's only if you have base e. Now I have base a. And and that, well, you're okay, Lynn. You're all right. So base a could be any number. A could be any number. Okay. Well, I got to be a little bit careful here. I got to be a little careful. I want to say one thing on that. I want to say one thing. We're assuming we are assuming that a is greater than 0. So I'm going to add that here. So this derivative of the function a to the x power assumes that your base a is greater than 0. And the way we're going to get this derivative, the way we're going to get it is we're going to rewrite a to the x power in terms of the base e. So if you were to take e to the log of a to the x power, that's just going to equal a to the x power. That's a fancy way of writing a to the x power. Now you might ask, well, why would you want to do that? Because well, we know how to find the derivative of e to the x power, and we know the chain rule. So I'm going to write a to the x power as e to the log of a to the x power, or I should say, I'm going to write a to the x power as e to the power log of a to the x power. But then remember, the log of a to the x power, that can be written as x times the log of a using the log rules. So now when I differentiate a to the x power, that's the same as differentiating e to the power x times log of a. Well, what special rule do I need to use to differentiate e to the power x log a? What special rule? That's right, Neil, the chain rule. Absolutely. Because this is the composition of two functions, an inner and an outer function. I mean, that's what the e to the x log of a, it's the composition of an inner and an outer function. What's the outer function going to be? Is the outer function going to be, okay, it's going to be e to the x power. Good, Sebastian. Good, Neil. The outer function is e to the x power. The inner function is x times the log of a. So by the chain rule then, the derivative of e to the power x log a is e to the x log of a, because we know that the derivative of e to the x power is just e to the x power. Okay, so the derivative, but now I'm using the chain rule, so I'm treating x to the log of a, x times the log of a, as like my variable. So the derivative of e to the power x log a is e to the power x log of a times the derivative of the inner function. The derivative of x times the log of a would just be 1 times the log of a. And so now we have a formula for the derivative of a to the x power. The derivative of a to the x power is a to the x times the log of a. The reason it comes up, John, the 1 times the log of a, is by the chain rule. Because you have to take, you took the derivative of your outer function, and that got you e to the power x log of a. But then you have to take the derivative of the inner function, which is x times the log of a. That's x times a constant. The log of a is a number, a positive number. So the derivative of x times the log of a would just be 1 times the log of a. Very good. Good question. And then that gets us here to our formula. So it's a formula that, I mean, you don't see it a whole lot, but it's actually a very important formula. And we'll note that the formula works for, like if you had, let's go back to the derivative of e to the x power. Now that's base e. So what if a were equal to e? I mean, a doesn't have to be, base a here doesn't have to be e, but what if it were? Well, if we apply the formula, we're going to get e to the x times the log of e. But what is the log of e? 1. So you get e to the x, as you should get. So this formula here is it's a general formula for the derivative of an exponential function. All right, are there any, of course, now we have to go and solve the problem, but are there any questions so far here? Okay, Anna, good. So I'm of course pleased to see that students are here in class. We have about 5 people out. That concerns me a little bit, but you're here and that's good. And certainly nobody's working on their homework now, right? That's another reason I deactivate homework during class time. I don't want, I mean, you're here for the lecture, and you're here and you're learning. And so you're not working on the homework now, so I don't want others to work on the homework now, Okay, let's continue on here. So now, here we go. The derivative of 2 to the 3 to the power 3 to the x squared, okay, Well, let me ask you this. Let me ask you this. So how many functions are there in this? How many functions are there? That's right, Nicholas. That's right, John. There are three. That's right, Zoe. Three functions. So what's the outermost function? You know, if you had like, you know, an H and an F and a G, and you had to describe the outermost function, that would be the H. What would that be? What would the outermost function be? Good, good, excellent. Sebastian, Lynn, and John, very good. That's 2 to the x power. Okay, good, Rodrigo. Now what's the next function? What's the next, like moving inward, what's the next outer function? Good, everybody, 3 to the x. Good. See, very good, very good. And then what's the innermost function? What's the innermost function? Obviously x squared. Very good, everybody. Very good. Very good. And so we're going to use the chain rule here. We're going to use the chain rule. And the first link in your chain for the derivative is going to be 2 to the power 3 to the x squared times log of 2. And then the next link is going to be the derivative of 3 to the x squared power. Finally, the derivative of the x squared, which is 2x. I mean, it's really kind of hard to, you almost have to, I think the fact that you understand what the, you know, three functions are going from outer to inner, hopefully you're okay with this answer. But let me give you a moment to think and see if you have any questions. Zoe asks, is there any way to simplify it more? No, this is as good as it's going to get. And this is what you would type in WebAssign. How many notice that when you type an answer in WebAssign, all right, Zoe, and you know, you have to like, it can be a little bit complicated. How many notice the calc pad pops up? How many have seen that when they type an answer? Sometimes the calc pad tops. Yeah, the calc. So that's right, even Nicholas and John. So yeah, the calc pad's designed to help you make it easier to enter answers in. So that's what the calc pad's there for. Okay. All right. And incidentally, all right, so are there any questions on this before we move to the next example? All right, we'll go ahead then. Thank you, Betsu. We'll move to the next example. Incidentally, class, I want a quick mention. So on your first exam, some of you like have it like, you know, you shared your OneDrive with me, but I'm getting like notifications, like reminders that you shared your OneDrive with me on the exam, and so you can turn that notification off. You don't have to, now that exam one's in the past, perhaps you could go into your OneDrive and deactivate. There must be a, is there a feature where like after you submit the share your work on OneDrive, there's like a email reminder that I get? Is there a feature? There must be some feature. Is anybody aware of that? Um, or is that like, did anybody like Ian has no idea on that? Well, you know, maybe it's just an automated thing. But okay, no problem, no problem, no problem. I'm not as worried about getting reminders that you sent me your work than, you know, you submitting your work right. So we won't worry about that. Okay, very good, very good. Let's move on to the next problem. All right, take a moment to copy this down. Okay, so we have here, we want to find the derivative of the function y equals the sine of the tangent of the square root of 1 plus x cubed. Okay, so we want to find the derivative of this. And when you look at this, you know, the chain rule, the reason they use the chain is because you can think of it as like links in the chain. So like the last problem we did, there were three functions, and so that required us to take three derivatives and three links in the chain, three derivatives moving from the outer to the inner function. How many derivatives are going to be involved here? How many links are there in the chain? How many different functions are there? Okay. Nicholas thinks 4, Ian thinks 3. We're getting some different answers. Well, all right. Kelvin thinks 4. Anna and John think 3. Lynn thinks 3. So you have the sine. Betsua thinks 3. All right. We're getting a variety of answers. Very good participation. Oh, man. Rodrigo thinks 5. Okay. So, all right. Well, we'll see here. So you got the sine and the tangent. Okay. What's next? Going from outer to inner. That's good. The square root function is next. And then finally, the last function is 1 plus x cubed. So there are four functions. There are four functions that are involved in this chain rule. So there's going to be four links. Are there any questions on that? All right. Thank you, Anna. All right. Well, then let's go ahead and work out the chain rule. So the first thing I do is the square root of 1 plus x cubed. I write that as 1 plus x cubed to the half power. I like to do that because then I can apply the power rule. Makes it, I like the power rule. Well, now we're ready. Now we're ready to work it out. And all, I'm just going to show you the answer here. And of course, for your next exam now, this is the kind of thing I want to see, right? So the derivative of the sine, in terms of your work, this is what I'd like to see. Derivative of the sine is the cosine. Derivative of the tangent is secant squared. The derivative of something to the half power is this here. And then finally, the derivative of 1 plus x cubed is 3x squared. Let me give you a moment to copy it down, and let's see if there are any questions on that. All right. Are there any questions in general on what you're seeing here? Are there any questions on the chain rule? You can see there are four links to the chain. Here's the first link. Here's the second link. Here's the third link. And here's the last link. Naturally, it might make sense to simplify things a little bit. So generally, I like to put my square roots back in the So my derivative, y prime, is equal to the cosine of the tangent of the square root of 1 plus x cubed times secant squared of the square root of 1 plus x cubed times 3x squared over 2 times the square root of 1 plus x cubed. How many think this last form looks kind of beautiful, looks kind of nice? I think it has a nice look to it. I like putting in the square roots. Sure. Nicholas agrees. Anna agrees. Thank you, everybody. Nicholas and Anna. Now, one thing I'll mention while I'm at it. So in WebAssign, you have to be careful when you have the tangent of something. So like WebAssign might require, like if you had to type in your answer, to be safe, I think it's best to put parentheses around your angles. Okay, I think it's good to put parentheses around your angles. So like the tangent of the square root of 1 plus x cubed, I put parentheses around the square root of 1 plus x cubed. And the secant squared of square root of 1 plus x cubed, I put parentheses around that. Okay, how many notice that it's usually safest to put parentheses around your angle in WebAssign, like when you type your answer? I don't know if I've seen, like for instance, the sine of theta. Oh, Nicholas, does it do it automatically? Does it put parentheses around the angles automatically? Okay, well that's great. That's great. Okay. Well, I'm liking that. All right. Are there any questions? So Ian says when you type in the trig function, it does the first parenthesis. So then, Ian, you have to add in the last parenthesis. You have to close it manually. Okay, all right, something to keep in mind of, you know. Let's see, Lynn asks, how do you explain the square root part? All right, so good question, good question. So the 1 plus x cubed to the half minus 1, that's the same as, well, that's the same as 1 plus x cubed to the negative half power, right? And so that's the same as 1 over 1 plus x cubed getting better with this mouse to the half power. And now, Lynn, you're comfortable with the result there. All right, excellent, excellent. Yeah, I would recommend that you write your answers in simplified radical form in WebAssign, just because it's something. I mean, WebAssign would likely take this answer, okay, with the powers in it and all, but it's good to get used to putting the square roots and cube roots back in, whatever, put the roots back in, because it just makes the answer a little more comfortable, I guess. It gives it a more comfortable look. And all right, well, if we're good on this, then let's move to the next problem. If there are no questions, we'll move on. Okay. All right. That's multiplying by 1/2 is, let me just go back here. Right, 1/2 is like two's in the denominator. Two's in the denominator, like 1/2, two's in the denominator. So 2's still in the denominator in the final answer. So that's right. That's right, Lynn. All right, let's do another example from 3.5. Let me give you a moment to copy the example down. Okay, so in this problem, we want to find the equation of the line of the tangent line to the parametric curve described by the parametric equations x equals 2 times the sine of 2t and y equals 2 times the sine of t at the point root 3, 1. Where does this curve have horizontal tangents? Okay, so how many recall graphing curves with parametric functions back in their pre-calculus class? This should be review. How many recall seeing this? I've taught pre-calculus at Montgomery College, and well, I've taught it in a lot of places. And all right, so there are a few people where maybe this is seems a little bit new. All right, let me just show you what goes on here with this. I'll bring up the whiteboard. I'll bring up the whiteboard here. All right, hold on here. Let me bring up the whiteboard and I'll give you an example of putting something in parametric mode. Okay, so we have here an x-axis and a y-axis. And what I'm going to do is I'm going to write down two parametric equations. First one is going to be x equals the cosine of t. The second one is going to be y equals the sine of t. Okay, two equations. So what this does is, I mean, we can make a little table here, and I'll show you how this produces a curve. Okay, so I'm going to make a little table. And I'm going to pick values of t. Let me just kind of separate this. I'm going to pick values of t. And when I pick a value of t, I will be able to find a coordinate xy. So like when t equals 0, okay, when t equals 0, all right, for that value of t, x is going to equal the cosine of 0, and y is going to equal the sine of 0. Okay, Ian remembers it. All right, well, a little refresher, good. So what is the cosine? What is the cosine of 0 equal to? Think about your trigonometry. Does anybody remember the cosine of 0? It's going to be 1. All right, what's the sine of 0 equal to? Sine of 0 equals 0. So when t equals 0, the coordinate you're going to get is 1, 0. And so what I do is on my picture here, okay, if this is 1 here, I'll put a point there. And that point corresponds to t equals 0. So what we're going to do is we're going to vary the values of vary t, let t take on different values. And when we do that, we're going to generate different coordinates. So let's try t equals pi over 4. Okay, when t equals pi over 4, x will equal the cosine of pi over 4. Okay, we'll get to the y. The cosine of pi over 4, you should know what that is. That's pi over 4 is how many degrees? Pi over 4. Pi is 180 degrees, right? So pi over 4 is 45 degrees. What's the cosine of 45 degrees? It would be almost right, Zoe. I think you meant root 2 over 2. That's all right. And incidentally, the sine of pi over 4, the sine of 45 degrees is also root 2 over 2. And so now you've got a coordinate of root 2 over 2 and root 2 over 2, which is like 0.707 comma 0.707. If we plot that point, assuming that, you know, we'll put 1 here, put -1 over here, and 1, -1 there. Root 2 would be right about here. That goes when t equals pi over 4. What's maybe another good value? How about pi over 2? When t equals pi over 2, cosine of pi over 2 is going to give you 0. That's right, Zoe. And the sine of pi over 2 is going to give you, what's the sine of 90 degrees? 1. That's right, John. All right. Let me pick pi. Also, let me add that as a point. The cosine of 180 degrees is -1. That's right, Lynn. That's right, Zoe. And what's the sine of 180 degrees? 0. That's right, Lynn. That's right, Ian. And we could keep going. Let me go ahead and plot these last 2 points. Here's the 0, 1. Right here. And here's the -1, 0. Okay, and so you can imagine, you know, whenever you learn to graph functions, when you learned about graphing functions, you would find some points on the function, get an idea of what the function looked like, and you'd graph the function. Well, we're doing the same thing here with these parametric equations to graph the curve. What's this curve gonna what's the curve gonna look like, you think? And we didn't, you know, we can continue, it's gonna be a circle. That's right. And we can graph it, and I'm sorry my circle's not the prettiest circle, but this is what the graph's going to look like Forget about that line there. I don't know why that. I've seen this happen from time to time. These weird lines show up on the picture. I don't know. There's no tangent here right now. There's no tangent line. So just ignore that line. Okay, and of course, we can put an arrow on our curve to denote as time increases which way is the curve going. You know, think of like I'd like to think of like a fly or an insect. Let's say a fly or an insect moves along a curve that is that follows these parametric equations: x equals cosine of t, y equals sine of t. This is the curve that would be generated. So for different values of time, the flies at different points. So to start with, the flies at coordinate 1, 0, t equals 0. Then after pi over 2 seconds, the flies at 0, 1. Okay, so this is a very simple example of how to graph a curve with parametric equations. And how many, is this helpful, this example? Is this, how many does this ring a bell now? Good, Chaco. Good, John. Good, Anna. Excellent, 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 Zoe. All right, thank you, Ian. Very good, very good. So now your calculator, I don't want to take the time right now to do it on the calculator, but the calculator, if you go to mode, there's a mode button there, and on the fourth line of the mode button, your calculator's on function mode, but you can switch it over to PAR. PAR is parametric mode. And then when you go to the y equals, you'll you know, the y equals button where you graph functions, it'll have an x and a y for your parametric equations. And if you need to see on the TI-84 calculator how to graph a curve with parametric equations, you can just, you know, go on Google and type how to graphing a curve with parametric equations on TI-84 or 83 calculator. And believe me, there'll be a ton of videos that come up. How many have done that before to learn things on the TI-83 or 84 calculator? Gone to Google and typed in some keywords, and then you get a YouTube video. Okay, so you all know what I'm talking about here. You all know what I'm talking about. All right, so let me go ahead and get back to the problem now. Any other questions before we move on? I don't know. I have to worry. You know, you're here. And that's where my focus is. All right, so all right, so let me get back to the problem here. Okay, so now we did a very easy curve, a circle. We generated a circle with two parametric equations. But of course, the fact that x equals 2 times the sine of 2t and y equals 2 times the sine of t, the sine function for x and the sine function for y, they have different periods, right? They have different periods. So that's going to generate a more interesting function. So let me just move on to the solution here. So this is a graph of the parametric curve generated by x equals 2 times the sine of 2t and y equals 2 times the sine of t. And what I've done is I've put on the graph, so you know, here's the graph, the curve I should say. If you want to model things moving in space, parametric equations are very nice. So there's my curve, and the tangent, I've drawn a tangent line here that passes through, okay, that passes through the point √3 and 1. Okay. And √3 and 1 is on, it's on the curve. So they're not like for a specific value of t. Let me just see here. When for here, let's see here. Yeah, this would go for when t equals pi over 6. Because when t equals pi over 6, 2 times the sine of 2 times pi over 6 it's a 2 there. What I'm trying to do is I'm trying to justify to you why the coordinate square root of 3 and 1 is on our curve. And to justify it, you need to show that for a certain value of t, you're going to get an x coordinate of square root of 3. And x, remember, x is 2 times the sine of 2 times t. So x, in this case, if t is pi over 6, x equals 2 times the sine of 2 times pi over 6. Right? This is a 2 here. I'm trying to draw it best I can, class. That's a 2. Hold on. See, this is where teaching remotely takes a little bit longer than in class. Okay, you just copy it down, Rodrigo. You just copy it. It's in the recording, though. You don't have to copy it, but so you're going to get x equals 2 times the sine of pi over 3. Well, that sine of pi over 3, the sine of 60 degrees, is √3 over 2. So that'll equal √3. And then for y, when t is pi over 6, y will equal 2 times the sine of pi over 6. And that's just going to be, the sine of 30 degrees is half. So that's 2 times a half, and that's 1. Okay, so I'm just showing you why this coordinate √3, 1, this xy coordinate, why it's on our curve. And in order to show that that point is on the curve, you have to find a value of t such that the parametric equations x and y evaluated at that t value would give you this x and y coordinate, and this does. Okay, so now what we have to do is we have to, of course, find this tangent line, find the equation of the tangent line, And we can see the tangent lines there. It is a line. It does have some equation. So what do we have to find in order to get the equation of the tangent line? What do we have to find? We have to find, well, what's involved in finding, slope. We got to find a slope. We have a point. We have a point, we have a point on the line, but now we got to get its slope. And so this is sort of a repeat to what I showed up here. To find the slope of the tangent line at root 3 over 1, we need to find the derivative, dy dx, when t equals pi over 6. And again, t equals pi over 6 is the right t value because x will equal root 3 when t is pi over 6, and y will equal 1 when t is pi over 6. Let me give you a moment to copy that down. Now we go after the slope. So again, the slope that we want is the derivative when t equals pi over 6. But here's the thing. When you look at this, these parametric equations, do you have that y equals a function of x? I mean, do we have that? No, we don't have that. We do not have that. So what we have to do is we need to get an expression for dy dx. We need to get an expression for dy dx. And here's how we do it. By the chain rule, dy dt would be equal to dy dx times dx dt. And why is that? Why is this true? I just wrote this rule down. Dy dt equals dy dx times dx dt. Why is that chain rule correct? Good, Nicholas. The dx's cancel out. That's right, Betsua. That's right, Lynn. The dx's cancel out. Now, I'm not going to cancel them out, but I could. Well, they simplify out. I like to say simplify. So you get dy dt equals dy dt. What I'm going to do is I'm going to solve now. Now that I have a legitimate chain rule, I'm going to solve dy dx. I'm going to solve for dy dx. So dy dx would equal dy dt over dx dt. That's assuming, by the way, that dx dt is not equal to 0. Given that, with this formula here, I can find dy dx. Because x prime of t can be shown to be 4 times the cosine of 2t. And y prime of t is equal to 2 times the cosine of t. So now it's just a matter of plugging in the formula the dy dt and the dx dt. And so dy dx would equal 2 times the cosine of t over 4 times the cosine of 2t. And that'll simplify to cosine of t over 2 times the cosine of 2t. Are there any questions on that? So John, I think it'll be helpful to draw a graph. I'll have to think of it. John's asking for the exam, this kind of problem. Will I ask you to draw a graph? I might, but let me think on that a little bit over the weekend. Okay, good question. I can tell you a graph's going to be helpful. I can tell you that. Okay, so now what we need to do is we need to evaluate dy dx when x equals, or when t equals pi over 6. May I move to the next page? Are we comfortable? Okay, I'll wait a little bit. All right, Joe's good, all right. So I just use, the chain rule here, right? I use the chain rule right there. All right, Sebastian, you're good? Are there any questions? All right, well then let's move on. So now I can evaluate the derivative dy dx at t equals pi over 6 just by plugging in pi over 6. And when I do that, you're going to get root 3 over 2. And so now you can get the equation of the tangent line, which you've done, How many times have you found the equation of a line in your life? How often would you say? It's been quite a while, quite a bit, all right? Now, incidentally, the tangent line on the graph, if you look at that graph, if you go back to the picture, well, I'll let you copy this, then I'll go back to the picture. All right, so we get the equation of the tangent line as y equals the square root of 3 over 2 times x minus a half. So the slope of our tangent line is positive. That means is the tangent line going up or down if the slope's positive? Very easy question. Going up. Got to go up. If the slope were negative, the tangent line would be going down, but this is going up. Okay. And if you go to the picture, here, the tangent line is indeed going up. And notice that the intercept as well looks to be about negative a half. Here's negative 1. The intercept looks to be about negative a half. So this is an example where you could draw a picture, and it'll help you intuitively and graphically. It'll help you confirm your result. So like on the exam, a problem like this, you have 2 tries to get the answer right. Why not draw a graph? A calculator can draw a graph easily of any curve with parametric equations. Just draw the graph, and you could even, well, you could see if it makes sense. All right, now the other part of the question that was asked was, where does this curve have horizontal tangents? Okay, where does the curve have horizontal tangents? So clearly on the curve, horizontal tangents, and maybe I'll use blue here. Here's a horizontal tangent, and here's another horizontal tangent. So when it says, where does this curve have horizontal tangents, it's asking for the coordinates. It's asking for the coordinates. Well, if you had to guess, what's this coordinate here? What's this coordinate look to be? Yeah, 0, 2. And the other coordinate here looks to be 0, -2. Good. Okay. So let's see if we can confirm that answer mathematically. So tangents for, that's tangents, hold on. Tangents for the curve will be horizontal for certain values of t when dy dx equals 0, right? Because if the derivative is 0, the slope is 0, and so that would be a horizontal line, a horizontal tangent. So it is necessary that the derivative be equal to 0. Okay, to find the horizontal tangents. And that would have to occur when the numerator equals 0, but the denominator can't be allowed to be 0. So what we're doing is we're finding t, values of t, when the cosine of t equals 0. That's really what we're finding. And then we're going to double check and make sure the cosine of t is not 0. Well, based on your trigonometry knowledge, the cosine of t equals 0 when t is 90 degrees and t is 270 degrees, when t is pi over 2 and t equals 3 pi over 2. Those are the values for the cosine that make the cosine equal to 0. If you graph the cosine function, if you just graph it on your calculator, you'll see at pi over 2 the cosine is 0, and at 3 pi over 2 the cosine is 0. Okay, so that means then that the curve is going to have horizontal tangents when t equals pi over 2. Okay, so well, when t equals pi over 2, there will be a horizontal tangent at that point. And if we evaluate that point, we put in the t equals pi over 2 into the parametric equations, and we'll get out 0, 2. The other point is t equal, or the other time, I should say, the other time, the other value of t is t equals 3 pi over 2. And that's going to happen. That's going to happen at 0, negative 2, because we just put in 3 pi over 2 for t in the parametric equations, and we'll get 0, negative 2. So this mathematically confirms what we saw geometrically on the picture. All right, please let me know if you have any questions. How many think this is pretty cool? Yeah. I mean, you're doing some really cool stuff here. Oh. Joe says no. Well, you know, you're maturing mathematically. JK, what's that stand for, Joe? JK? Oh, just kidding. Okay. All right. All right. All right. You want to be engineers and scientists, right? This is what they do. Engineers, computer programmers, you know, you have to have a good analytical skills. All right, well, if there's no more questions, I'm going to stop the recording.